Hi, my name is Hussain, and I'll present our work towards orchestration of complex networking experiments. This work is based on a tool called Magi that has been used in the DETER testbed for 7 years for the evaluation of large systems, integrated system development, and education. In this talk, I'll first explain what I mean by an experiment, what are the sources of complexity within networking experiments. I'll then present a solution, Magi, discuss how it's used in several case studies, provide some retrospective takeaways before I conclude. What do we mean by a networking experiment? The goal of a networking experiment is to conduct realistic evaluations of systems on a testbed. Researchers use the testbed for testing and tuning their systems, but in order to do that, they first need to create representative scenarios. These scenarios are mesoscale models of the internet or enterprise networks with a wide variety of topological conditions and application mixes. The goal of a networking experiment is to understand how their system behaves in these conditions in order to optimize the performance of their system. What makes an experiment complex? First, the systems under test rarely are a monolithic system. They have many distributed parts and are typically an integration of technologies from different sources. These distributed parts of the system can be configured in multiple ways and are coupled with a wide variety of background traffic and many application mixes. The goal is to evaluate the performance of the system under stress. For example, what is the maximum volume of traffic that a server can handle through a bottleneck link? Fundamentally, the goal of a networking experiment is to help the developers identify corner case performance issues that would be otherwise hard to track or identify and tune their systems for it. This is especially important in cybersecurity experiments where systems can exhibit a wide range of unanticipated behaviors during an attack, which can only be seen in testbed-based evaluations. Finally, the goal is also to get statistically sound results and ensure repeatability and reproducibility of these results. Hence, it's important to create an executable configuration so that the experiments can be repeated several times, not only by the researchers, but also by other researchers and students. Our goal with Magi was to enable such complex experiment orchestration. That is the ability to execute a sequence of steps that capture the idiosyncrasies of a representative scenario in a repeatable manner on the testbed. There have been several tools that support experiment orchestration and experiment lifecycle management in a variety of testbeds. I'm going to mention a couple of tools here. First is experimenters typically are computer scientists themselves, and it's really hard to get them to adopt new tools. One of the most popular way to run experiment continues to be through shell-based scripts and SSH-based scripts. They're highly brittle mechanisms to run experiments with limited repeatability, and very rarely do they have an ability to report errors and check for validity of experiments. Another popular mechanism seems to be using Ansible-like configuration management tools. While these tools have a rich tool set, they have limited expressibility, which is required for the complex experiments as I just described. There have been several testbeds in the past. Each testbed has had its own experiment management and orchestration tool. DETER also had a first generation point and click tool called Sphere. We subsequently developed Magi, which focused mainly on scale and repeatability and automation of experiments based on our learnings from Sphere. In Magi, experiments can design a wide range of scenarios using a library of traffic agents. These scenarios can then be executed on the testbed by an orchestrator and Daemons. Next, I will discuss the key highlights of the Magi tool and how it supports orchestration. The design. Magi fundamentally has two parts: design and execution of the experiment. The design of an experiment starts with the conceptual model and is translated into a YAML-based specification. this translation, this definition of specification is done by the experimenter. And the specification is a sequence of steps that describes one individual run of the distributed system with a specific set of parameters, configuration of the background traffic components, and mapping of the components to the topology. Next, we'll look at what the specification looks like in detail. The specification for a Magi experiment consists of 5 key directives: group, agent, event, event streams, and triggers. Groups are a mapping of all the behavior roles in the experiment to physical and virtual machines. This is the only place in the orchestration where the orchestration is coupled with the underlying topology. The agent directive is a pointer to the code implementation with the execution arguments. Agent is launched typically on a group of nodes. For example, here, the HTTP client implementation, which is identified by the path, is launched on the client group of nodes, along with the execution arguments. Once the agents are launched in the experiment nodes, the orchestrator can use the event directive to direct the agent. Each event directive typically maps to a method that can be invoked within the agent and can accept parameters. Collections of events are ordered as event streams, which formulate the experiment behavior. In this case, we see a separate event stream for the server behavior and a separate event stream for the client behavior. Event streams are coupled based on triggers, which provide synchronization points. Triggers can be time-based synchronization points or event-based synchronization points. The examples there show both event-based, a condition-based synchronization point, as well as a time-based synchronization point. Once the specification is defined, this specification is executed by the orchestrator and the node daemons in the experiment. We'll discuss the orchestrator in detail next. The orchestrator is the heart of the Magi tool. It is the command and control center for orchestration and consists of 3 main parts. There's a parser that reads in the experimentation scripts and identifies the event streams and provides an ability to schedule the different events. This parsed script is passed to the scheduler, which essentially starts a thread to handle each event stream and sends events to all the nodes in the experiment in an asynchronous manner. That means the events are non-blocking, and once an event is sent out to all the daemons, the scheduler can move on to the next event in the event stream. The evaluator receives return values from the nodes in the experiment, correlates these responses, and if there is a trigger which is based on the return values, it then coordinates with the scheduler to make sure that the event stream is correctly satisfied and can move on. The Magi toolkit also consists of daemons, which are lightweight control conduits on the experiment nodes. The daemon is responsible for receiving events from the orchestrator and launching and controlling the agents on the nodes. It takes in the return values from the agents and sends it back to the evaluator for trigger evaluation. And finally, the agent modules are implementation on the nodes. These are Python-based implementations on the nodes for a particular behavior within the experiment. Next, we'll discuss several case studies, how the Magi system was used for experiments on DETER. First, we looked at education. Magi has been extensively used on the DETER testbed to support classes, graduate and undergraduate level classes. In the example in the paper, we discuss how it was used for an undergraduate class, Introduction to Computer Networks, where the students were assigned to build a multi-user text-based chat client and server system. And using Magi, this project was developed over the semester where there were multiple milestones where the students could evaluate their client implementation with the server, random client implementation with the student servers, and also run a distributed system with 30 clients supported with the student server. And these kinds of evaluations would be extremely hard to do without a system like Magi. The other case study that we present in the paper is where we enable feedback loops being created within the experiment. These are typically used when different teams are interacting within the same experiment, but have limited access to different parts of a scenario. So in this example, we have 2,000 web clients, 1,000 control clients, which connect, and 1,000 control clients, which connect to an Apache web server farm. And the web clients continue contacting the server farm. And the goal of this experiment is to ensure that a particular bottleneck link has traffic, has 100 megabits of traffic always passing over the bottleneck link. So the Magi system has essentially an agent that senses the traffic on the network, then devises a compute strategy to either increase, decrease, or maintain traffic based on the sensor signal it receives, and then actuates a control action to either increase the amount of traffic at the control clients or reduce it based on what the current network conditions are. The other example is where 5 teams developed adversary-resistant communication to circumvent censorship on Tor networks. The Tor, which is a very large system, we use Magi to configure, deploy, and manage the Tor system, as well as 5 different technologies that were deployed on it. These were experiments that had ranged from 10 nodes to 100 nodes on the system, and the Magi agents had completely orchestrated the experiment from not only bringing up the full Tor network, but also deploying the technologies by the 5 teams and ensuring that there was cross traffic, which included microblogging, voice over IP, and file sharing applications. And lastly, we also have supported cyber-physical system experimentation on it, where we are monitoring the impact of a denial of service attack on damping oscillations, power flow oscillations in the presence of these attacks. So where there is a IEEE 39 power bus, which is overlaid on an 18-node communication topology on DETER, and then subsequently has a wide mix of background traffic as well as attack traffic to study the impact of the attack on the power flow oscillations. The Magi, as I mentioned earlier, Magi is a second-generation command line-based tool for orchestration on DETER, which we've used over the last 7 years. And based on my experience, we had several key takeaways. First, we found that the topology agnostic ability of Magi allowed experimenters to experiment with small-scale experiments and then directly use the same specification and apply it to larger scale experiments. And that feature was very widely used by most experimenters as they scaled up their experiments on DETER. Additionally, the event streams that enable unordered events and synchronization points enabled a large level of concurrency and asynchronous operation between the orchestrator and the daemons, and allowed experiments to execute rapidly at scale. And finally, getting the systematic feedback from the daemon for any errors and failures significantly helped debugging errors within the experiment, as well as supported graceful failure degradation in case of unrecoverable errors, which were critical again for experimentation at that scale. Finally, to conclude, I want to say that Magi has made it significantly easier to run large and complex experiments. In addition to DETER, we have used it on Emulab and Genie and other smaller testbed environments. The code is open source and available, along with detailed documentation and worked out experiment examples at the links below. Thank you so much for listening to my talk.